Implicit differentiation. We can find the rate of change or the tangent line slope to curves when they're not functions. For example, the curve x cubed plus y cubed equals 6xy. We can find the tangent lines to that at a lot of different places. But because it's not a function, the tricks that we've learned so far don't really apply that well. So we're going to try and find dy dx when x cubed plus y cubed is equal to 6xy. We take the derivative on both sides. Notice that we've got a sum rule on the left side, and we've got a constant multiple rule on the right side. Some of these derivatives are easier than others. The derivative of x cubed, for example, is 3x squared. The derivative of y cubed is 3y squared times dy dx because y depends on x. And the derivative of x times y is a product rule. So it's going to be u prime times v plus v prime times u, for u equals x and v equals y. And so on the right, we end up with 6 times 1 times y plus the derivative of y is dy dx times x. Move the dy dx terms to the left side. We end up with 3y squared times dy dx minus 6x dy dx equals 6y minus 3x squared. Factor out the dy dx and divide through by the square bracketed term. And so dy dx is going to be 6y minus 3x squared divided by 3y squared minus 6x. Another example, we want to find dy dx when y to the 5 plus y plus x is equal to 0. So we differentiate both sides. The derivative of y to the 5 should be 5y to the 4 times dy dx. The derivative of y should be dy dx. The derivative of x is 1, and the derivative of 0 is 0. So we get 5y to the 4 dy dx plus dy dx plus 1 equals 0. Move the 1 to the right side, factor out the dy dx. Divide through by the square bracketed term, and we get dy dx is equal to negative 1 over 5y to the 4 plus 1. In this example, we want to find dy dx when the function is x plus 1 to the 10 times x squared plus 1 to the 11 divided by x cubed plus 1 to the 12. Now, if we were to differentiate this just using the typical ways that we normally differentiate things, we have a product rule on top and a quotient rule overall. Each of those product and quotient rules is then itself a chain rule. So this could become very complicated very quickly. However, if we let y equal x plus 1 to the 10, x squared plus 1 to the 11, divided by x cubed plus 1 to the 12, and we take logs on both sides, we can use the properties of logs to break up the right side of the equality. Because the log of a product is the sum of logs, and the log of a quotient is the difference of logs, our right side becomes log of x plus 1 to the 10 plus log of x squared plus 1 to the 11 minus log of x cubed plus 1 to the 12. We can further take advantage of the log properties by remembering that if we have a log of something to an exponent, we can bring the exponent out front. So this simplifies the right side a lot. If we differentiate both sides then, the derivative of log y is going to be 1 over y times dy dx. And we differentiate each term on the right to get 10 divided by the derivative of log of x plus 1, which is 1 over x plus 1, plus 11 times the derivative of x squared plus 1, which is 1 over x squared plus 1 times the derivative of x squared plus 1, minus 12 times the derivative of log of x cubed plus 1, which is 1 over x cubed plus 1 times 3x squared. If we multiply through then by y and back substitute what we defined as y, we get our final answer. So in this example, we've used the property of logs and implicit differentiation to make this derivative significantly more straightforward.